In this module, we're going to look at intermolecular forces and the role they play in determining some of the properties of some of the solutions that we look at. Several announcements. So Chapter 16 homework, that's due on Sunday the 19th. We finished Chapter 16. I'll have a review session Friday morning at our normal scheduled class time, 10 to 11:30 a.m. And then I'll also have the review session Sunday as well, 8 to 9 p.m. Both of those sessions will be recorded and made available. The study guide's posted on Blackboard, so is the practice exam, and I'll post the answer key after our review session on Friday. The midterm exam is on Monday, July 20th. It's open for 24 hours. I will give you the equations you'll need. I'll give you access to a periodic table. Please do not use other sources. You can use your notes, you can use the book. Please do not go to other sources and Google and spend hours looking for these answers. So the material that we're going to cover today will be on the final exam, but is not on this midterm exam. So this will be new material that is not covered on the midterm exam. So before we get started, I wanted to take a look at two different videos and try to explain the observed properties that we see in these two videos. And for the first video, I ask you, I'm going to propose, this experiment. We're in space, and we take a droplet of water in space and we hit it with these ping pong paddles. What happens to that droplet of water? So does that droplet of water, does it scatter all over the place? Does it bounce back and forth? What happens to a droplet of water if you hit it with a ping pong paddle in space? And so we're going to watch a video of Scott Kelly doing that demonstration, followed by another video of another astronaut doing another demonstration with water, looking at how water behaves in space. And so while you're watching these, think about, why is that occurring? Why is water behaving the way it does? And if one video is fun to watch, it doesn't hurt to watch another. So this is a Canadian astronaut, and he's going to perform an experiment where he saturates a towel in space and then proceeds to wring that towel out. So trying to squeeze all the water out of that towel. And so let's just watch and observe how water behaves and how that might be different than how we know water to behave here on Earth. And so both of those videos demonstrated the power of intermolecular forces, and that's what we're going to be talking about in this lecture today. Intermolecular forces, and they're going to help us understand why different molecules or different elements take different phases. And so we can look at this by looking at three halogens. So all three of these samples are halogens. We have diatomic chlorine gas, we have bromine, which is a liquid, and then we have solid iodine. So all three being halogens, and yet under the same temperature and the same pressure, same conditions, all three take a different phase. Chlorine being in the gas phase, bromine being in the liquid phase, and iodine being in the solid phase. We're going to try to answer, how can that be? Why are all three occupying a different phase under identical conditions? And the answer is going to be intermolecular forces. So what about those intermolecular forces allows one to be a gas, one to be a liquid, and one to be a solid, all under the same conditions? And just remember, when we're talking about these different phases, certainly we could change temperature, we could change pressure, and that would allow us to interconvert between these phases. In the gas phase, we could do that at high temperature. We could move most samples into the gas phase. We could cool down that gas, cause it to condense into a liquid, and then if we kept cooling that liquid, right, we'd form a solid. Where the main differences between these three phases are essentially how much movement is taking place, how many intermolecular forces are present, and how far apart are these molecules. So when the gas molecules, the molecules are very far apart, they're moving very quickly, we're going to have the lowest degree of intermolecular forces. The solid molecules, on the other hand, they are hardly moving at all. They're very close together, and we're going to have the highest degree of intermolecular forces because those molecules, right, are right next to each other. So they can maximize their attraction between each individual molecule in the sample. That's hard to do in the gas phase when things are flying all over the place very quickly, all different directions, and they're very far apart. So to try to figure out why something is a gas when something else is a liquid and something else is a solid, all under the same conditions, we have to look at two different things. We have to look at what is the kinetic energy of the sample, so in the gas phase, I have a high average kinetic energy. The molecules are moving very quickly, they're very far apart, they're moving all the time. Whereas in the solid phase, I have very low kinetic energy, right? Kinetic energy is the energy of movement. So I have a low kinetic energy in the solid phase. Those molecules are very close together and not moving much at all. And the next component that we have to think about are, what is the strength of intermolecular forces within the sample? So what is the attraction? What are the attractions between each of the individual molecules in that sample? The stronger the attraction, right, the closer I'm going to pull those molecules together. The weaker the attraction, probably the farther apart those molecules are going to be. So now I've mentioned it twice, but what are intermolecular forces? Intermolecular forces are highlighted by this interaction right here between the hydrogen and the chlorine in a molecule of HCl. Intermolecular forces, they are forces between two different molecules atoms or ions. And they are temporary. This is important. Temporary interactions. And that's not to be confused with intramolecular forces. So think about the difference between intercellular and intracellular. It's the same thing here. Intermolecular force is between two different molecules. Intramolecular is within a molecule. So forces within the same molecule. And we know intramolecular forces as covalent bonds, as an example. Right, so an intramolecular force would be this hydrogen-chlorine bond. That is a permanent bond between hydrogen and chlorine, and it's within that molecule. It's holding that molecule together. Whereas an intermolecular force is between two different molecules of HCl, between the hydrogen on one and the chlorine on the other. That's the key distinction between an intramolecular force and an intermolecular force. So all of this lecture, we're going to look at examples of intermolecular forces and how they help determine the properties of a sample. So these intermolecular forces, they are relatively small in nature, right? Individually, they are weak. We're going to look at things on the order of 1 to 15 kilojoules per mole. But they are cumulative, right? So overall, these forces are really important. These forces help determine things like boiling point, melting point, viscosity, and surface tension. So individually, on a case-by-case basis, these interactions are weak. But cumulatively, if we think about an entire sample where there's thousands and hundreds of thousands of these interactions, that interaction and each individual interactions and the energy of each of those individual interactions, they add up to determine some very important properties of that solution. So we're going to talk about 4 different interactions. We're going to talk about hydrogen bonding, which is on the scale of 15 kilojoules per mole. We're going to talk about dipole-dipole interactions at 5 kilojoules per mole. London dispersion forces, the weakest at approximately 1 kilojoule per mole. And the 4th one we're going to talk about is ion-dipole interactions, which are also on the order of 15 kilojoules per mole. So again, are we talking about big energy or are we talking about little energy? Are these energies big or small? Right, these energies are small. And just to show you a comparison to help let you see the scale of these energies relative to energies we're used to talking about, the energies of covalent bonds. Right, we're talking about intermolecular forces on the order of 1 to 15 kilojoules per mole. Here are some energies of covalent bonds. Covalent bonds, right, just an example of a carbon-hydrogen bond, 413 kilojoules per mole. If you want to get to double and triple bonds, right, here's 614, 839 kilojoules per mole. So these intermolecular forces, they are small energies, but they are important because they're cumulative. They add up. They are much less than the energy of a covalent bond, as we can see here, but they are still important because they help determine the properties of a sample.